So today I'm going to do two pretty quick ones. First one will be post-hoc comparisons, then we'll talk about transformations. Maybe I had it in the opposite order. I don't know. It doesn't matter. Makes more sense to post-hocs first, I think. So let's say you've got a significant F, right? So you've done your analysis of variance, you've done your 4 groups or 3 groups or whatever. Now, remember the HO was U1 equals mu2 equals mu3, blah, 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 u sub k. In other words, all the means are equal. That's our null hypothesis. So if that's our null, then the alternative hypothesis just is that 2 of those are different. It doesn't say which 2. And you might wonder which 2 means different. Because let's say you have different levels of some variable, and it could be whatever. I mean, I don't know, different amounts of alcohol given to people, say 4 groups, and number of words recalled, memory test. Well, it might be after a certain point, it doesn't matter how much alcohol you have. Like, there's no difference between 3 drinks and 4 drinks. I don't think that's actually true, but let's pretend. It might be the case that you have 3 control groups. If you ever had a study, doing drug studies with non-humans, you often have, if you're with the rats on some drug doing something, and then you've got the rats that got no drug, and then the rats that got a sham drug, in other words, they were given a saline, right? Just vehicle. And there's another group who were picked up and shown the needle, but not given the needle. So it's like 3 controls. There you're not interested if the control groups differ at all. What you're interested in really is, does the treatment group differ from all the control groups? Right? So when you do ANOVA though, it's not telling you which mean differs from which other mean. Right? So we need a way to do that. The first way that people came up with, really I think is the first way, was the Barbary Correction. What this is you do t-tests, and if you did regular t-tests between groups, your alpha level goes up because you keep getting like 0.05 and 0.05 and 0.05, and eventually you get a really big number. So the Barbary Correction just takes care of this by taking the alpha level and dividing it by the number of contrasts you're doing, and then it changes the critical t-value. That's all it does. So you take the number of, so it's 1 divided by the number of comparisons you're going to do. So it's doing 3 comparisons, 1 over 3, a third, times the alpha. So in other words, instead of 0.05, now it's 0.05 divided by 3. And for two or 3 comparisons, that's probably fine. But the difference, not the difference, but what's the word I'm looking for? The critical t-value starts to get really, really big if you start using, let's say you had 10 comparisons you have to do. Now suddenly your comparison is at 0.005 instead of 0.05, your critical value. And if you take a look at a t-table, you'll see there's a really big difference between 0.05 and 0.005 in critical values. So this works, there's nothing wrong with it. And it used to be a lot more difficult to do these complicated tables. Now, of course, a computer will do this for you. In SPSS or PSPP, you just choose comparisons, and you do an analysis of variance, and it'll do one of these post-hoc comparisons. So it's just a t-test. The difference is what we're using on the bottom, on the denominator. Numerator, denominator, yeah. Still have to do that. It's called TPrime, and we're doing 2 times the mean squared error over n. Oh, remember, mean squared error is just the standard deviation. Right, you're comparing 2 groups, so it's mean squared error 1, mean squared error 2. It's over n because you have the same number of subjects in each group. It's always better if you have the same number of subjects in each group. It would change slightly if you had different numbers of subjects in each group. It would be mean squared error over n1 plus mean squared error over n2. N2, sorry. Typically, you're going to have the same number of subjects per group. So you get this T-prime, as it's called, and you just compare it. Okay? This is one of those things that literally nobody does by hand. Because you can just click, oh, I want comparisons. There's other things, if you wanted to say, oh, also, is this group different from some arbitrary number, you can actually just do a regular old t-test and use mean squared error as the variance. So if you want to compare it to, say, 50% for chance or something, I've done that, and I've done that by hand. But typically, no one does these things by hand. Oh, here's another version. This goes by very quickly. I'm just going to show you a bunch of formulas. No one's ever going to ask you to calculate this. Because, again, it's there already to do it, right? So this is something called the studentized range. This is the largest mean you want to compare minus the smallest mean you want to compare. Okay? And you divide it by the square root of mean squared error over n. And you get something what's called a Q value, which you would never report in a paper as a Q value. I don't know why that's the way it works, but that's the way it works. You just say, I used a studentized range, and I found that these groups were different. This then gives you a value for how big a range two things have to be different by to be significant, to be considered different. So if it gives you 7, and 2 means different by 7, well, if it gives you 7 and 2 means different by 7, but by greater than 7, they are now different. Just gives you a value.
What is X bar S?
I'm sorry?
What is X bar S and X bar?
Oh, X bar sub L is the largest mean you're comparing, and X bar sub S is the smallest mean. So let's say that 10 means you want to compare. But you just say, what's the largest one, what's the smallest one? And this just gives you, then you get this number, and let's say it's 7 as a result. You then say, oh, it's 7. Any means that differ by 7 are different from each other. That's all it does. Here's another one. This is called the McCools test. It gives you, what you do is you get a value, you look it up in a table, right? For the number of comparisons you're doing, that's what R is. So this value you actually look up. And at the 0.05 level of significance, and the degrees of freedom for error. So you look that up in a table, and you multiply that value times the square root of mean squared error over n, and you get a value called W. It's another one of these range things. So it gives you a range. So let's say you get 6. Now any means that differ by 6 are significantly different. I wouldn't worry a lot about how these things are calculated. No one really does. It's a matter of which one do you want to use. This is a really commonly used one in all kinds of literature. So it's any set of comparisons with range R. In other words, how big do you want it to be? Okay? Don't worry about how you calculate these things. I will say that some of them are really conservative and some of them are really not conservative. This strikes the balance nicely, McCools, of being roughly in the middle. The most conservative test, except that like if you do a Barbary, you're doing 10 comparisons. But the most conservative test, I'm not going to tell you about it, it's called a Chiffre test, because no one does it. The least. So yeah, anyway, so I'll take a sec. All comparisons with a range of 3. So anything 3 or bigger is different. Tukey's HSD, you know what HSD stands for? Honestly significantly different. That's what he used, which is pretty great. It's another common one. And it just uses the largest possible range, the biggest possible difference between two groups. So two groups, let's say they differ by, let's say what you're interested in is the two groups differ by 10. You look and go, I have two groups here differ by 10. I'm going to look up a Q value for 10.05 plus the right number of degrees of freedom, and then I can see if they're different. And then anything 10 or bigger is different. And you look it up and you get this value. So McCools, Tukey are pretty commonly used. Like I said, there's one that is so conservative that I didn't mention, and it's called a Chiffre test. And I didn't mention it because no one uses it because, in fact, what it'll do is you'll get a significant F, and then it'll tell you that none of your means are different. So it's so conservative that it says, no, you was wrong. And you don't want that either. But you don't want something that's going to say, there's all kinds of differences that aren't really there. You want something in the middle, and student McCools, the McCools test is the one that I've always used. So the question you always get asked is, which one should I use? Here's a secret. Most people do them all, and then pick one. You really probably shouldn't do that. You should pick something in advance and say, I don't mind if it's a little bit there's going to be a few too many false positives. Or I want to be very conservative. You should pick that in advance. You shouldn't do what's called, this is kind of like what's called p-hacking, which is when you just keep doing stats until you find what you want. You really shouldn't do that. That policy. Stick to one within a paper. And I have seen, when I review articles for journals, which I do all the time, I have seen cases where people change post hoc tests they use within a paper. And that to me is a pretty big red flag. That's me saying, oh, I figure hypothesis here, but you change statistical evidence here because it didn't work. So you want to stick with one. And as I said, I've usually used HSD, to use HSD. Because it's sort of in the middle. I'm actually typically not, that is a sort of philosophical thing, if you can get philosophical with post hoc tests. If you're really interested in two groups being different or three groups being different, why don't you just do some t-tests and not do any of them? If you're interested in the pattern in your data, the overall pattern, and you're saying, is the pattern different than what I would expect? Yeah, then it makes sense to not do post hocs frequently, right? So as far as I'm concerned, I think it makes a lot more sense just to do the ANOVA and say, look, here's the pattern I found. It's pretty obvious what the difference is. I have one group that's up here and all the other groups are down here. I don't really care if those groups differ from each other. I just don't care. It's pretty obvious where the difference comes from. This one group is way up here, the other groups are way down here, right? That's a philosophical thing, and that's sort of I'm more interested in overall patterns of data than I am interested in, is this group different from this group? This group? And believe me, I have this fight almost every year, first of all, with my honor students, but secondly, with my colleagues when we do the psych honors thesis day, and they all get up and speak, and it's psych and biology now, we go together, and when psych students practice, I know biology students too, but they don't go to those practice talks, they go to psych ones, and they get really worked up about post hoc tests, and I'm always like, why do you care? Who cares? Why don't you just pattern your data? It's different than they're all the same. So you found something, interpret it. But I run up against a brick wall, which is most of my colleagues, well, all of them. So I just, because it's not a hill I want to die on kind of thing. But I don't think they're that important. That's why I've spent all of 15 minutes in the course talking about them. And there might be one little question in the next quiz, what's a post hoc test, but I'm not going to teach any more about them. If you need to do them, you can take comparisons and you will get to them. All right? Questions about post hoc tests?